Hey guys, hello everyone. Welcome to Rasayan Academy once again. So we are here with another video, and in this video we are going to start the solving the questions of June 2015 and December 2015 CSI net papers. So I hope that you have seen these questions already, and as the video proceeds, you can just stop the video and try to solve these questions by yourself. Okay. So the first and a very easy question that we start with is right over here. Following reaction goes through. Okay, so this is another very simple name reaction. Okay, I hope that you identify this reaction, and the question is very simple. The following reaction goes through a free radical intermediate, and the name of this reaction is Hunsdiecker-Borodine reaction. Hunsdiecker-Borodine reaction. Although this reaction is asked in lower levels, usually in the CSI net, it has been asked in June 2015 only, not later than that. Okay, so let's discuss the reaction over here. Now, what is this reaction? Very simple. When you are having a silver carboxylate salt, this way, if you are having a silver carboxylate salt, Ag plus and COO minus like that, it is going to, it is basically going to, let's say, break this bond, and the Br minus is going to break this bond over here. The carbonyl group is going to attack the Br positive, it becomes Br positive, and Br minus is going to leave. So what is the overall reaction if we want to see it over here? You are going to have one CO OBr bond like this, and one AgBr minus has been precipitated. This is your precipitate, and this is your oxygen bromine bond. Now this bond is basically going to break homolytically, and it gives you carboxylate radical and a Br radical like this. Okay, so this is what breaks homolytically in the presence of sunlight, okay, or in the presence of light. Very simple reaction. And you have a free bromide. Now what is this free bromide going to do? First of all, you are going to break this molecule, the carboxylate radical, into a 3-degree radical. Now yes, you are having a radical on the bridgehead position, right? And to this bridgehead radical, your Br is going to react, and it is going to finally give you this molecule. Okay, so it is not impossible to generate a radical on the bridgehead position. Why? Because this need not be planar. Radicals, it's not necessary that radical should be planar. A radical could still be pyramidal, just like ammonia, and it is still stable. Okay, so radicals flip in between these two structures. Okay, it is always like that. Radicals are sometimes planar when they want to do resonance, and sometimes they are pyramidal. So it is okay like that. Okay, so it's not like carbocation that it cannot be planar. So free radical intermediate is involved, Hunsdiecker-Borodine reaction, and this is your answer to the first question of June 2015. Next question on name reaction June 2015 is, the major product formed in the following reaction is. So once again guys, this is a very simple reaction, and I have made you do this, so I hope that you'll be able to solve this by yourself. In the first step, you have the hydrazine. Uh, Basically, you have the hydrochloride salt of the hydrazine. Okay, so what is that going to give you? It is going to, hydrazine is going to make hydrazone molecule. The rest of the molecule is as it is. You are going to make the hydrazone molecule from here, N, NH, and H like this. Okay, and in the presence of triethylamine, what will happen? The proton is removed. You are going to break the bond in this way, and the epoxide is going to open up. When the epoxide opens up, let's say this methyl is like this, double bond, N double bond N H. This is O minus. Rest of the molecule will be as it is. So this epoxide has opened up, and it is going to take a proton from the protonated triethylamine base. Yes, it can exchange the proton from there. So ultimately you are going to have this molecule. Okay, I'm writing it over here. This is your molecule ultimately. Which name reaction is this? Have you identified it yet? Right. and one more base molecule, triethylamine, is going to remove this proton. Now this proton is very acidic over here. Why? Because when it is removed, the whole nitrogen molecule can be removed and gives you, and it eliminates the nitrogen gas. Okay, that is the driving force of this reaction, and it is going to give you a negative charge on the double bond. This negative charge can further take away the proton from the protonated base. Okay, so this is it. This is your product. Okay, so from this molecule, what have you got? You had this alpha beta epoxy carbonyl, which has now got reduced to the allylic alcohol over here. This is your Vatin reaction. It is Vatin reaction, and it is a modification of the Wolff-Kishner reduction, in which you are still having the hydrazine molecule, but you don't have the alpha beta epoxy molecule, right? You only have a ketone, and in the presence of hydrazine and your base molecule, that is potassium hydroxide, you get the reduction. Okay, but here it is rearranged product that you are getting, allylic alcohol Vatin reaction. Asked in June 2015. So the answer should be this one, option number C. Okay. Next question is very, very simple, guys. You have to just match the column A with column B, and these are all coupling reaction, palladium catalyzed coupling reactions. So let's see, guys. For Suzuki coupling, you have an organoborane compound. So this is it. You have an organoborane compound over here. I think this is very easy for you also, right? So just do this complete match the following. Sonogashira coupling happens with the terminal alkynes. Okay. Negishi coupling, you require the organo-zinc compound. Alright. And for the Heck coupling, you require an alkene. Okay. So this is what you have. 1, 2, 3, and 4 are occupied. For the fourth reaction, which is using tin, organo tin, you are having the Stille coupling, but then it is not given in the question, so it's okay. Your answer is option number A for this one. 1 matches with 2, 2 matches with 1, and 3 matches with 4, and the fourth one is going to match with E over here. Okay, very simple. So these kind of questions might also appear right in your exam. Just match the following with name reaction, try to remember them. Another question from June 2015, the major product formed in the following reaction is. So a very, very important name reaction once again, palladium acetate, PPH3, and triethylamine. So here you are having this leaving group on the allylic position. Whenever you have a good leaving group on the allylic position, you are going to think about one particular name reaction, which is going to have the pi allyl complex formation. What is that name reaction, guys? Absolutely, it is the Tsuji-Trost reaction. Okay, it is the Tsuji-Trost reaction. Okay, asked in June 2015. So whenever you have this kind of a species, first of all, your double bond is going to coordinate to the palladium. Okay, and palladium will always remember wherever the leaving group was. Let's say it is above the acetate group, palladium is going to attach below. Okay, it is going to attach below in this way, so that when the nucleophile attacks, okay, such that when the nucleophile attacks like this on the pyrrole system, once again the palladium will remove from below the plane. Okay, so yes, the nucleophile is present in the molecule itself, nitrogen, and the double bond is going to eliminate this way. Okay, so there is your nitrogen, it has still attacked from above. I have directly removed this proton because now the N will have a positive charge in this way, right? And the triethylamine is going to replace it. Okay, so you can just remove this proton directly. Okay, now be careful that when the nucleophile is attacking from above, the palladium once again goes below, and it is going to detach from the molecule, and your product should be option number B. That is the product of Tsuji-Trost reaction. Both the hydrogens are going to be below. It is also a coupling reaction, just a little bit different. Next question that you see, June 2015, is the structure of A and B in the following synthetic sequence are. So the first reagent is that of, this is an ylide, and what kind of ylide is this? CH3P, and this is a double bond with CH CO2Me. So this is a stable ylide, isn't it? It is a stable ylide. What are stable ylides, guys? You consider the double bond to be like this, minus and plus. That is what a double bond is basically. Yes. So the stabilized ylide is one which can resonate the negative charge into some electron withdrawing group. And we know that the stable ylides most of the times will give you the E alkenes when they are reacting with the carbonyl, free CHO group. Okay. So this upper reaction, the first reaction is Wittig reaction. Very, very simple. Let's try to draw the product A for it. Okay. So the Wittig reaction, guys, it is going to give you this way. Wittig reaction is going to give you an E alkene. Alright. So the alkene was already present over here to the CHO molecule. This is your carbon. This is your same carbon and having a hydrogen over here. So I'm going to add one CH in this way and the CO2Me group like this. This is your molecule. Okay. Also, in the presence of heat, what happens? In the presence of heat, the acetate part of the molecule is going to eliminate, and you are going to generate this kind of a molecule. So how do I write it? This can be written in this way: N double bond, all right, N double bond, and this double bond O, CO2. I mean, this is trans. Okay, I have written the molecule in the S trans form. Now, the second step of this reaction is going to be a Diels-Alder reaction. In the presence of heat, you know that you have got a 4 plus 2 cycloaddition possibility. So absolutely you are going to get a Diels-Alder reaction. Diels-Alder reaction, option number A, will give you one 6-membered ring, which is not present in A. So this is wrong, which is not present in C. This is also wrong. It could be anything from B and D. So we are going to move onwards with that. And yes, and you know what happens is in this question you see, without even drawing the product, you see that okay, next molecule, next reagent is LiLH4. So by LiLH4, the reduction should happen, and you cannot get this carbonyl. So we are thinking ki chalo D cannot be the answer, right? But we still have to confirm B. Okay, even we are thinking about this. So how is it going to be? You can just draw this molecule in this way first of all. CO2Me, just take care this is trans, and also take care that this bond is also trans, but then you have to write the carbon nitrogen in this way. Okay, how many bonds in between, how many carbons in between? 1, 2 and 3 carbons in between. Okay, so yes, this is it, 1, 2 and 3 carbons in between. You are going to do the Diels-Alder reaction in this way, 4 plus 2 cycloaddition, and yes, one ring formed on this side, CO2Me, one double bond. So see, both of these hydrogens are on the same side, and that is what is giving you the stereochemistry, because on the other side you have CH2 and nitrogen, no stereochemistry problem. So both of these hydrogens which are reacting to give you the new junction, they are going to be absolutely cis. They are going to be on the same side. Yes. So that's it. You have this CH2 over here, the hydrogen, let's say it is below, this hydrogen, let's say it is also below, so you are going to get the new ring junction this way. Okay, one carbon extra, isn't it? 1, 2 and 3. Yes, 1, 2 and 3. There should be a nitrogen over here. Okay, nitrogen is on the center. Alright, this is what you have. Just a second. Nitrogen is over here. This is your molecule. Okay, so that's exactly what we get over here, just that you have to reduce the carbonyls, both of the carbonyls, guys. So the ester as well as the ketone, lithium aluminium hydride reduces both of them, followed by hydrolysis. Your answer is absolutely option number B. Okay, that is what we were suspecting before also, but we have to confirm our product. So yes, B is correct. Okay, Diels-Alder, first is Wittig reaction, and then Diels-Alder reaction, then reduction. Okay, next is this question. Major product formed in the following synthetic sequence on monoterpene polygon is. So this is your monoterpene, and yes, try to do this question by yourself. Very beautiful question. What is the Br2 going to do? This is your CH3 carbonyl. So Br2 can give you anti-addition onto this alkene system, isn't it? Can give you anti-addition on this system, followed by sodium ethoxide can promote Favorskii reaction, because on the other alpha carbon, see, one alpha carbon has a proton, the other alpha carbon has a bromine. Yes. So this is how you're going to form a cyclopropanone molecule, intermediate basically. Now this ethoxide is once again going to attack over here. Okay, and the ring has to open up on this side. Why? Because there is a leaving group. So if the ring is opening up on this side, it is going to be driven by the leaving of your Br. Okay, so you have one CH3. Alright, so just do the numbering 1, 2, and 3. On the third position, you have both of these groups, and here is your C double bond OET, which is going to be further, converted into this molecule. Which one? Yes, this bond has to open up from here, so this is on this carbon. Yes, absolutely. Option number B. It is going to be converted into B. Okay, so OH minus is going to attack on this carbonyl, and it is going to give you the ester hydrolysis. So this is your answer. Now, what about the stereochemistry, guys? The only one correct answer has this trans stereochemistry, but it is very obvious, isn't it? That if the methyl group is above, if the methyl group is above, the carbon-carbon bond formation which has taken place, right? The acid is going to definitely transfer below. That is going to cause less steric hindrance to both of these groups. Okay, so answer is B. Now moving onward to December 2015. Very nice questions we have seen in this paper. The major product formed in the following reaction is. So you see the first question. Now, just by looking at the combination DMSO and COCl2 oxalyl chloride, you might be thinking about the Swern oxidation. But let's see, are we doing oxidation or something else? So this is a very nice question, guys. DMSO and COCl2, what is the process? Yes, this is dimethyl sulfoxide, for example. Dimethyl sulfoxide in the presence of oxalyl chloride. Okay, that's let's say this is one oxygen, double bond O, one more Cl. Sulfur has got a positive charge over here, so the free Cl minus it will attack on sulfur. The bonds are going to open up in this way. You have chlorosulfonium ion like this, plus CO2 plus CO plus Cl minus. Okay, this whole molecule is going to fragment. Alright, so this is your chlorosulfonium ion that you are getting, and what usually happens, the OH is supposed to attack on this sulfur, and it is supposed to give you this intermediate. Alright, because the Cl is going to eliminate now, so you have this once again the sulfonium ion like this. But then what happens is you are supposed to take this at a minus temperature. Okay, you are going to do this reaction at a very less temperature only in the Swern oxidation, and you also require a base. Let's say you require a base, triethylamine, for this. What is the base going to do? Base is going to remove a proton from here, and then it is going to make the carbonyl, but you don't have a base over here. If you don't have a base, then in the absence of base, no oxidation happens. In the absence of base, the chloride is going to attack on this carbon, because now the oxygen is a very good leaving group. It has connected to sulfur, and this is your product that you are getting. Okay, so unfortunately the product is this is no oxidation over here because you don't have a base. So in the Swern oxidation you require a base, otherwise it is going to be just like your nucleophilic substitution reaction. Okay, and it is going to give the byproduct your DMSO molecule once again. So D is the correct answer in this case, right? Be careful about this. Swern oxidation, very, very important question. What are the necessary conditions? The examiner can play with your mind. Alright, another very simple question. Major product formed in the following reaction is, so you can do this by yourself. You just have only one carbon which can be enolized. The other one has two methyls, right? Say I'm drawing this way. Going to attack on this carbon because there's a bromine leaving group, and now you must have got the hint. What is this name reaction? Absolutely Favorskii. Oxy minus going to attack over here, and when this carbonyl, when this OMe is attacking over here, the bond has to open up. Now let's say the bond has opened up on this side. Okay, we are going to consider both the possibilities. This is it. Let's say the negative charge has fallen over here. If this happens, the negative charge can fall back and it can give you a more substituted alpha beta unsaturated carbonyl. Okay, yes, right. This double bond, this is only one carbon. This is what you get. You can get an alpha beta unsaturated compound. All right, let's see one more possibility. Yes, if we are getting this possibility, your answer would be option C. But one more possibility over here from the same is, let's say the methoxy is attacking on this carbonyl and the bond opens on this side. So if this happens, you are just going to end up with ester and CH2Br, because there the other side you are not going to have any elimination possibility. Okay, then the D would be your correct answer, but we are not going to consider this because this is a less stable possibility, and this is entropically favored because one Br minus also eliminates over here, although it is going through a less stable carbanion 3 degree. But anyways, it can also happen in a concerted manner, and maybe you're not getting the carbanion. The product is option number C only. More substituted alkene part and alpha beta unsaturated carbonyl system. Next important question, December 15. Major product A and B in the following reactions are. So you see guys, a very, very important name reaction over here, that is scope elimination. Okay, we have done these reactions, scope elimination, and yes, let's see what's happening over here. First of all, try to, whenever you see the stereochemistry problem, try to draw the conformation. So this bond, this is above, this nitrogen is above, and the nitrogen is above and the oxygen is above like this, O minus. So cope elimination goes through a 5-membered transition state. Okay, and here you have two possibilities. As you can see, the nitrogen is above, so the O minus is also going above. Above there are two hydrogens to be eliminated. there is a hydrogen over here which is also above, and there is a hydrogen over here which is also above. So from these two hydrogens, since the temperature is high, we are going to follow the more stable product. Okay, so which is the more stable product? The hydrogen over here, if it is eliminated. All right, so O minus, if it is eliminating this proton from this side, then it is going to form the Sadzef alkene, more substituted alkene. Okay, and that is going to be the major product over here. In option number A, you are getting the major product like this. Okay. In option number B, if you draw the same molecule, draw the molecule in the same way. Now what happens is your nitrogen N oxide is present below. Alright, it is present below the plane. It only has one possibility. Now the temperature doesn't matter over here because you don't have a thermodynamic stability property over here. Only one kinetic alkene is going to form. Alright, so that's why you are going to get this alkene. Alright, so your answer has to be option number C. You only have one possibility. Okay, so the reaction is hope elimination. Both of these reactions are going to give you the same product. In option number B, there is only one possibility. Okay, in this way, and in option number A, there are two possibilities, but it selects the more stable possibility, this hydrogen. So the answer will be the same. Okay, very well. We move onwards to next question. I know this video is a bit lengthy, but yes, you are doing plenty of good questions. So don't forget to like and share and give a thumbs up also. Okay, the major product formed in the following reaction is, now guys, identify this reaction by yourself. We have done plenty of pericyclic reaction. Yes, what name reaction is this? You have seen the orthoester over here. So orthoester is just like an acetal. Okay, in the presence of acid, let's say I have protonated this oxygen. So in the presence of acid, it is going to eliminate one of the methanol molecules. This is OET, oxygen P positive, and this OET. One ethanol molecule has eliminated from here. Alright, this is your orthoester. So orthoester now is going to be attacked. Let's say it is like this. Now the orthoester is going to be attacked by the alcohol in this way. The bond falls back and one of the OET will also be removed. I have done the same step in just one step. So what I mean to say is, even if OH attacks, one of the group is going to be eliminated. Yes, positive, like this. Okay, now a proton from here is going to leave and give you this molecule. Just take care of the stereochemistry. This is what you have now. And what is this molecule, guys? This is your allyl vinyl ether system. Alright, okay, the double bond has to be over here. So alright, this is your double bond over here. So this is your allyl vinyl ether system, and the reaction is a Claisen reaction. Which Claisen? It is Johnson-Claisen, because it is going to give you an ester molecule as the product. Okay, 3 sigma tropic, 1, 2, 3, and 1 and 2 and 3. 3 sigma tropic rearrangement. What about the stereochemistry, guys? It's so obvious. You don't have to draw the 6-membered ring transition state. It is very visible over here. That is, when you're shifting this bond and when you're doing this transition, the carbon-carbon bond is going to be transferred from above. Okay, so we can just directly write it that the carbon-carbon bond is going to transfer from above and you are going to get this molecule. Okay, so the answer is absolutely option number C, and this is your Johnson-Claisen. That gives you the ester. Now, big molecule over here. This is our second last question. Following transformation involves sequential. So now you have to answer this question once again based on pericyclic reaction. See. So what is happening over here? Okay, this might look like a bit difficult, but it is not. First, identify what is given. So you have, if you want to check out for the Claisen rearrangement, let's say you want to check out for the Claisen rearrangement first. So for the Claisen rearrangement, you need the allyl vinyl ether. Do you have it? Let's check. This is allyl part, but this is also allyl part. So till now you don't have the allyl vinyl ether. So A option cannot be possible. You don't have the allyl vinyl ether. Cope rearrangement के लिए you are going to look for the 1,5-diene system. Do you have the 1,5-diene? Let's check. So 1, 2, 3, 4 and 5. Yes, you have the 1,5-diene. Maybe cope is possible. Let's try to do this. Let's try to do the cope rearrangement from the first. Okay, so we are just trying to. Alright, or what I should do is I should write this molecule in a little bit this way so that you are able to correlate nicely. Your double bond, just let's keep this methyl away and let's keep the double bond over here. The bond formation possibility. Now it is going to be easier to understand. Okay, so there is going to be a double bond over here, one double bond over here. Carbon just got attached to this one. Now this carbon still has and a double bond like this. Now you can say that you have the allyl vinyl ether system. Now look at this part. Look at the oxygen, this carbon, this is your vinyl and this is your allyl system. So first you did the cope rearrangement. Now secondly you do the Claisen rearrangement this way. I'm not doing any kind of numbering guys because then we will lose the essence of this reaction. That would be a lot of process to do. That's why I'm directly doing it. Okay. This is the skeleton. You have a double bond O now over here. Okay, and here from above the plane only you are going to attach allylic system CH2CH, right? So okay, now the last step the last step that we want to do is the ene reaction, because first we have got the cope. Claisen is also possible after the cope, and last thing that we can try out is the Claisen. Right over here is the ene reaction. The hydrogen will transfer onto this oxygen and let's say, yes, how does the ene reaction work? This bond carbonyl carbon and this oxygen is going to take this. Let's say this is the direction. Okay, after that you are exactly getting this molecule, but if you want me to write it, H2 of the molecule is as it is, have one carbonyl, have one bond over here. So this is a cyclohexane system. Also, it's not very beautiful, but absolutely it is cyclohexane. You are having 6 carbons over here. You can draw the molecule in this way. All right. So what have we got? We have got the Pope rearrangement, Claisen rearrangement, and the ene. Okay, all of them in this one question. Very beautiful question, December 2015. Last question for today. The major product A and B in the following reaction sequence are. So you know this reaction very nicely when you are getting the ylide, or let's say this is not yet the ylide, it can be formed as the ylide CH2H positive on sulfur. Now the NaH, that is your hydride base, is going to take away this proton from here, and then you get the sulfoxonium ylide. Okay, then you get the sulfoxonium ylide, which is going to be transferring the CH2 minus to the 1,4 position, right? It is going to always do the 1,4 attack. Always 1,4 attack, the sulfoxonium, if there is a possibility. So it is going to attack over here, the bond opens up, falls back, it is going to give you cyclopropanation. Where does it do the cyclopropanation? Methyl is below, so definitely the group is going to attack from above. So it gives you cyclopropanation in this way. Gives you cyclopropanation of this CH2 group in this way. This is your CH2. Alright, this is correct. This is wrong. No epoxidation going to happen. Also, the CH2 is not transferred below because of steric repulsion. So it's very evident that the answer is option number A only. But let's look at the next reaction. That is lithium in liquid ammonia, which is Birch reduction type. So when you are having this molecule, okay, it is not alpha beta unsaturated carbonyl. Lekin, even if you want to do Birch reduction or reduction of this system, how is the electron going to be transferred? Let's see this. Okay, so the electron will be transferred onto this carbon so that the bond opens up from here and give you the alpha beta unsaturated system, or let's say the enolate anion, like, yes, you get the methyl radical and then you get the, okay, the radical and the negative charge wants to stay as far apart as possible. So this is it. The O minus can resonate back, it can tautomerize back to give you the carbonyl system over here, just that your methyl radical is going to take a hydrogen. This is CH3. Alright, the CH3 will be above, it should be above always, and the carbonyl is going to form the tautomerism. So this part is going to do the tautomerism, and this part, the stereochemistry, is as it is. So your answer is this one, option number A. This is your correct answer. Alright guys, so we have done plenty of questions. 11 or 12 questions, I guess. Okay. And the questions are really important. More PYQ questions are coming up on the same topic of name reactions. Please try to solve them. This one is Korechkovsky reaction, first name reaction video. I'm going to see you all in another very nice video just like this. Please keep practicing. Also keep